Hey, AP Chemsters, this is Mrs. Vanderlei bringing you Chapter 5.3, Blank Wall. So we left off talking about the relationship between pressure and volume, and that was Boyle's law. And we had said that if pressure goes up, volume goes down. That was an indirect relationship, so we multiplied. So now we're going to talk about Charles' law, and how is that different? Well, Charles was a Frenchman. He was a hot air balloon enthusiast. He was doing his, science stuff at the height of the hot air balloon. Actually, the first hot air balloon exhibition was in Paris, and Benjamin Franklin was actually there to witness it, surprisingly enough. So it may not then shock you to realize that Charles was interested in the volume and the temperature relationship. He's watching the hot air balloons, all right? So you fill up the balloon with, yes, hot air. What happens to its volume? It expands. So he hit upon that. And so he said that was a direct relationship. So what did you do? You did a divide, okay? So the plot of volume and temperature is a straight line because it's a direct relationship. So V1 divided by T1 equals V2 divided by T2. So here's the graph here. Oops, come on down. There you go. So here he plots his different gases. Notice that different gases, probably all 1 atmosphere, have different lines, and that's okay. And he had a couple of inspirations here. So when it got so cold, maybe like around this area here, he couldn't actually plot the graphs anymore, so he extrapolated each graph. And notice when you extrapolate, that means to plot beyond, his measurements. Notice where they all end up. They all end up at negative 273.2. And so he hit upon that must be the lowest temperature. But he has a little problem. If he's going to put these numbers in his equation here, when you hit a negative 10 Celsius, what does that mean? You can't have a negative volume. If I were to do my math, if this is a positive temperature and a positive volume, what if to make this equal, your volume would be negative? Or more interestingly enough, what if it were 0? What if he measured this at 0 degrees Celsius? Well, what's wrong with that? Can you divide by 0? Well, of course you can't. That's an undefined number. So when he extrapolated each of these graphs or each of these gases down, they all came to the exact same point of negative 273. To satisfy his equation where any number would then work, he said, okay, let's add 273 to all Celsius numbers, and you'll never have to worry about a negative value. The only thing you might have to worry about is where you come right here, and that would be at 0 Kelvin. So Kelvin is equal to Celsius plus 273. If my lowest temperature is negative 273, then you could have Kelvin equals 0. Kelvin is named after Lord Kelvin. The Kelvin scale is known as the absolute scale, if you ever heard that before. And so the absolute 0 is the lowest temperature. So let's just check this out. I think I've already given away all the answers here. So what is the temperature when the volume extrapolates to 0? It's negative 273. And note the temperature scale. What is that in Kelvin? It's 0. It doesn't say okay, that's 0 Kelvin. Interestingly enough, if I were doing this right, I'd have the little degree sign I put up here. That would have gone here. So Celsius does have degrees Celsius, but Kelvin does not. There is no degree symbol, so it looks like okay. So anyway, where are we right now? Have we ever hit absolute 0? Not here on Earth, actually, because what happens at absolute 0 is that all motion stops. All motion, like, what kind of motion are we talking about? Well, it's not going to go from one place to another. It's not going to have any rotational motion. It's not going to have any vibrational motion. That's the typical motions that atoms do. And also, the electrons quit spinning. Oh, so we have in today's technology gone to a fraction of a Kelvin, but it's still not 0. They cannot make it cold enough, if you will, to even make the electrons to quit spinning. So that's where we are right now. So here's another Nobel Prize idea. I'm just giving you all sorts of ones, aren't I? That if you want to get that Nobel Prize, get it to be absolute 0 and make some kind of note that, yes, the electrons are truly quit spinning. I'm sure you'll get a Nobel Prize. You're going to shake the King of Sweden's hand and just remember me in your speech. Okay, that's all I ask. You don't have to give me money, I promise. Okay, so anyway, that's where we are in today's thing. We have never achieved absolute 0, just barely off because of those dang electrons. You know what I mean? All right, let's see what problem number 4 has to say. So it says a sample of gas, what's it doing, has at 15 degrees and 1 atmosphere, has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So here's my temperature, right? And here is my pressure. That's, oops, don't do that. I want a pressure. I'm trying to make a P here. There we go. So here's my pressure. There we go. And here's my V. Now what changed? Looks like temperature has changed, hasn't it? And my pressure, oh, my pressure didn't change, but they're looking for a new volume. So nothing's going on with pressure. Pressure is constant, right? So I have a change in temperature from 15 to 38 and a change in volume, 2.58 to, I don't know, that's what you're looking for, right? So what's the relationship between volume and temperature? I think it's direct. Think of your hot air balloon. What happens when it gets hotter? It expands. That's a direct relationship, so you're going to divide. Now, we have a little problem here. What unit did I give this in? I gave it to you in Celsius. What must you do every single time? Did you all catch that? If you're ever given a temperature in this entire unit, what must the unit be in? It must be in Kelvin. So you have to add what? 273 to everything. So my V1 is 2.58, my V2 is 288. How did I get to 273 to 15? So what am I looking for? I'm looking for V2. My V2 is right here. How did I get 311? I think that's what 38 plus 273 is. Okay, so how am I going to solve for this? I think you have to crisscross and divide. So why don't you go ahead and do that? And voila, I got 2.79. But Mrs. Vanderwalle, temperature only has 2 sig figs. I know, but what happens when you added to 273? What's the rule for sig figs? It's that least significant spot. So I have to go to the nearest tenths. That's why 288 has 3 sig figs, all right? And that was what I was using to solve for my volume. So I'm going to stick with my 3 sig figs, all right? So what should you be asking yourself? What is the check you need? What did temperature do? Temperature went up, right? So what should volume do? Should volume go up? Yes. Did it go up? Yes. Okay, and there you go. So what about problem number 5? It says, let me scroll it up. An ideal gas is in a cylinder at 2.5 liters, the temperature at 25.0. The gas is then heated at the temperature of 100.0. What is the volume of the new gas? So why don't you go ahead and set this up all by yourself, and let's see how you do. All right, so again, you're talking about volume and temperature. I plugged in my values. I added 273 to both sides. And I really should have had maybe 298.3 and 373.3, if you will. But did it really make a difference in the long run? No, because how many sig figs should my answer have? 2. Why 2? Because of the 2.5 liters, all right? So my answer is 3.1 liters. Does this make sense? Temperature went up. So volume should go up, and hopefully, yes, it does make sense. Okay, hopefully you did that right. Let's go on. All right, so Gay-Lussac's law, guess what? He knew Jacques Charles. He was another hot air balloon enthusiast. They were colleagues, if you will. They were contemporaries. I think that's the word I was looking for. And so his work was in pressure and temperature. It's the same idea. So if pressure goes up, temperature is also going to go up. So it's another direct relationship. The plot of pressure versus temperature will be a straight line. And there you go. I believe this is all consistent with what your last, the introductory lab was. Hopefully this is nothing new. How's that? So we don't have any new problems with it. You set them up identically to the Charles's law. All right, you'd have to divide P1 divided by T1 equals P2 divided by T2. Hey folks, what unit must temperature always be in? Yes, Kelvin. All right. So here's another one, is the combined gas law. This is probably a little more realistic because it's very difficult to keep either the volume constant or the pressure constant. So what happens if everything changes, all right? Well, you notice that the P1, V1 are still multiplied, but they need to put temperature on the bottom. It's combined of the Boyle's, Charles, and Gay-Lussac's law. So if you can recall, if temperature is constant, then it's P1, V1 equals P2, V2. if your pressure is constant, it's V1 over T1 equals V2 over T2. And if your volume is constant, then it's P1 over T1 equals P2 over V2. So it's a true combination of those three laws. Just make sure temperature's on the bottom. Make sure you use Kelvin, okay? So let's check out problem number 6. All right, what do we have here? And this is where it might be handy for you to jot down what you have. You have a contained, oh, this is a volume, and look at that, that's a milliliter, that makes sense. And this is a what? This is a temperature, it's 30 degrees, row, and a pressure, here's a pressure of 710 torr. You have a new volume, and you have a new temperature, okay? So what are we solving for? We're solving for the new pressure. So hopefully you can see kind of what all goes together and where, okay? So here I have it all worked out for you. Hopefully it's nothing too difficult. So here's my equation. Here's my 710 torr. Here is my 500. Why does it have a little line over the 0? Because that's your significant number, because it's 5.0 times 10 to the second mils over 303. Where'd that come from? That's your Kelvin, of course. You're looking at the new pressure and 25 mils. Boy, that volume went way down, and boy, that temperature went way up. All right. So when you do your math, again, how did I do that? I would do 710 times 500 divided by 303 times, remember we're going to cross multiply, times by 1093 divided by 25. So I ended up with that many torr, all right? Why do I have so many zeros? I couldn't tell you why I have so many zeros. I think that's kind of a mistake. How many zeros should I end up with? None. Here, let me fix that. Okay, very good. I fixed that. So I should have only 2 sig figs, because this has 2 sig figs, this has 2 sig figs, 25 has 2 sig figs. Your answer should have 2 sig figs. Phew. All right, here's another one, Avogadro's law. I'm not sure if you have done Avogadro's, but imagine if you have a balloon and you're blowing it up. So every breath of air you put in the balloon, what happens to the volume? It goes up. So as you add more moles into the balloon, the volume of the balloon goes up. Well, they both go up, it's direct. So notice I had to divide again, all right? So V1 over N1 equals V2 over N2. So how does this work? Well, let's take a look. Suppose we have a 12.2 liter sample containing 0.5 moles of gas at a pressure of 1 atm and a pressure of 25. If all this O2 were converted to ozone at the same temperature pressure, what would be the volume of the ozone? And so I wrote hint, write the equation first. Okay, I'll do that. So here's my equation, and I'm dealing with moles, and I have an equation, and I'm trying to find the volume of ozone when I'm given the volume of oxygen. What am I going to do here? I bet I need to set up a BCA table, don't I? I think I do. So here it is. So look over here first. I didn't bother hiding my other stuff. So here's my 0.5 moles of 3. So I need to go 0.5 divided by 3 times 2, and I get 0.33. So I have 0.33 moles of ozone. So if I have 12.2 liters over 0.5 equals what over 0.33? You end up with 8.1 liters of gas. But Mrs. Vanderwalle, you changed from oxygen to ozone. Can you do that? The answer is yes, all right? Because the point is, it doesn't make a difference what gas you have. It's that same relationship, okay? So we should be good there. Let's go on. Well, okay, let's not go on, because the next page is section 5.4, so this is a good place to stop. Like I said, as always, don't wait to be great. We'll see you next time. Bye.